Hi everyone, if you're not here and you missed out on class today, I hope this podcast kind of assists you. We're going to take a look at the lab and we're also going to take a look at the study guide and get as far as we can so that you're ready for your test next class and you're ready to turn in your final copy of your lab. So some students didn't quite finish the actual lab itself, and so they're finishing that in class. If that's the case and you're not here, please come in during like IC or lunch or before school or after school just to finish up your lab. All right, so let's just take a look. This is on the class website, and the lab handout is right here. That's number 3, and the rubric right here, that's down here at letter B, and I have them pulled up here. So what we're going to do is take a closer look at the rubric and discuss kind of points and how those points are assigned. So just taking a closer look here. All right, so the pre-lab, the background section, guys, a lot of people are not doing this. I need to make sure you are. Could you please make sure that you are using real examples for your 5 different types of chemical reactions? You should be discussing the 5 main types of chemical reactions and showing real examples. A lot of students are kind of confused on what that means. Like, what does it mean to have real examples in my background section? So on the lab handout itself, it was, there were certain areas where they actually show you real examples of various chemical reactions. So in the lab handout itself, if you look at equation 3, 4, and 5, those are all examples of synthesis reactions. And then equation 7 and 8, those are examples of decomposition. 9 and 10, those are examples of decomposition. 12 and 13, those are examples of single replacement. And then for double replacement, if you look at equations 15 and 16, those are great examples of double replacement. So, ladies and gentlemen, just make sure you understand that you need to have real examples. If you want to use the handout for your examples, go right ahead. But technically, if you use these examples from the handout, you should cite the actual handout in your citation. So we're going to take a look at that as well. What format are you guys supposed to be using for your citations? APA format. Examples, handout, publication. So using Google, you guys are so lucky that you guys get to look up anything you need whenever you want. I encourage you to continue to do that, but just make sure you're keeping kind of like a record of all the citations that you choose to use. Let's see, my favorite one to use, there was a good one. Let's see, I've got to find it. Okay, hold on. I think it was from... was it EasyBib? Yeah, EasyBib. And EasyBib, when you go trying to find out information about APA, it won't let you make an APA citation without charging you a fee. You actually have to pay for that. But what they do is they give you a guideline for free. So use the guideline. Don't pay money, guys. Don't do that. Don't do that. I don't want you to like spend any of your money paying for these things. But they actually have a whole like web page with full of examples and stuff on how to do APA format. Okay, so here's how to cite a website. Here's how to cite a blog post. I mean, they give you like a ton of examples just for free. And so I would encourage you guys to kind of dive in and see if maybe you can find some examples for free. So this is kind of like a journal, what you guys had. In my opinion, that's like a, oh wait, hold on, APA, sorry. I clicked the wrong link. What you guys have is kind of like a journal article, basically. That's what the handout, what I would consider the handout to be. So it gives you the structure, it gives you some examples here. And the last and first and middle initial, obviously that doesn't apply. But the year that it was published, the article title, the journal name, guys, you have all of that. So on the publication itself, let's see, hold on, let me get it. So we'll actually do this together so you guys can write this in. Let's see, let's go here. Okay. So the first thing that you are supposed to do on your citation is to do a last and first middle initial. We don't have that. That does not apply to us. If you go back to the article, there's no person, there's no main person that made this handout for you. But if there were, you would put that on there. Okay? So that does not apply. So we're going to go to the next step. Next step would be the year that it was published. All right, let's go check that out. Might be on the bottom. Let's see. 2009. Okay, so we're going to come in here. And I think this part has to be in parentheses if I'm not mistaken. I'll go back here. Yeah, so the year of publication has to be in parentheses with a period outside. So we're going to say 2009 and then end with a period. Okay, everyone doing okay so far? Easy. And then after that, we're going to say article title in regular type, not in italicized, not italicized or anything. So the article title, regular font, would be chemical reactions. So in regular font, chemical reactions. And I believe, if I'm not mistaken, it should end with a period. Yes, ends with a period. Okay. And then from there, the next step would be to do the journal name, and I think it's called FlimFacts something, we'll look at that, in italicized with a comma and the volume and issue. All right, so this would be Flynn Scientific Inc., or actually ChemFacts from Flynn Scientific Inc. And then over here, do you see the publication number? 4860. All right, so I'm going to call it ChemFacts exclamation mark. Do you guys see the exclamation mark? So this would be italicized, and for me, I'm just going to do cursive, okay? And it is an exclamation mark, so you have to put that kind of in there. ChemFacts. And then we're going to say Flynn Scientific. Is it two N's, guys? Thank you. Flynn Scientific. Oh, and by the way, when you go in a line, don't you have to do an indent? I think. Yes, we have to indent. So indent it here. Flynn Scientific. Flynn Scientific Inc. Oh, that should be an I. What am I doing? Inc. And I think pretty sure it ends with a period. Hey, have you guys ever learned this like in your science class? I'm just curious. Oh, it doesn't end with a period. It ends with a comma because we have to do our publication number or issue number. Okay, so the publication number is 4860. Let me see how they want that. You see how it says volume issue? We're going to say publication number because that's specifically what it says. So publication number 4860. Is that italicized still? Yes. So comma here. Okay. Oh, and a period for the ink. I'm sure that's proper, right? Because it's an abbreviation. So a period for ink and then a comma. And then we'll say publication, still in italicized. Publication number, what was it again? Do you remember? Say it again. 4860. Okay. And then for the pages, it goes PP and then pages, right? Luckily, we don't really have any pages. This is a full document, okay? If there's a specific area or region of the pages that you specifically looked at, you would include those pages just so that you can zoom in on exactly what pages you were looking at. But I think you use the whole thing, am I right? Yeah. So then just a period, I think. Let me just double check that. Yeah. Okay, so you decided your publication. That's probably where you're going to get most of your information from, right? Did anybody use a website yet? Okay, so come back up here, the APA guide. Let's see, we're going to go to website, and I'll give you some advice there. All right, so if there is a specific person who published that particular website, you would want to put their name. And if it's the name of a corporation, you might want to put the corporation's name, right? So last first initial. So if you want to pretend like you're using my website as an actual source, we can do that. So I'm going to give you some information about me. Last name Crowley. Okay. And then first and middle, I'll give you that. First is K, middle is C. You guys know way too much about me now. Year, month, date published. The most recent edit that I made on the website was, you know, you can just put, what's a month? April? You can put today, like, because I did edit it technically today. So let's go back one more time and make sure you're doing it right. Year, month, date published. Okay, so year, and this goes, does it go in parentheses? I can't remember. Yes, parentheses. So parentheses, year, 2017, comma, month would be April, and 7. Let me make sure the formatting looks correct. Yeah, I'm using this as a guide. You see how there's no comma between the month and the date. All right, end your parenthesis and put a period. All right, the title of my website, if you guys come back over here, the title of this particular area where you're looking at this content is Unit 6, and you have to be precise. You have to say exactly what it says for the heading of that web page. So Unit 6, you know, like this, hold on. Oh, and this is italicized, my bad. Unit 6, boop, boop. And then it says, in parentheses, HChem. And make it still like this. HChem. Come back over there. Colon, reactions. Colon, indent now. Reactions. Okay, and I'm pretty sure it ends with a period now. Yes, period. And then you can say retrieved from regular type, I before E, right? Retrieved from, and then I'm pretty sure you put the whole URL. Let me just check that. Yes. Oh, and don't say retrieve from, I'm sorry, don't do the, not that, this. Don't do this, my bad. Just retrieve from, and then you put the http:// www, blah, 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 blah. At that point, I would copy and paste from the website. All right, kind of nice, huh? All right, I hope your English teachers have not failed you, and hopefully, you know, you got a little lesson there from your science teacher. Woohoo! All right, are we all good? All right, I'm glad we discussed that because I want you to actually do a little bit of research. And so a lot of places in the lab, I'm sure you probably had to look up. So I do have some advice. If you want to go look at the handout of the lab, let's just kind of check that out. All right, so when you look at the handout, this particular area was probably a little hard for you guys. Predicting what the products were for questions 2, part A through H. Right? Predicting what the products are, balancing the reaction, and telling me what the reaction type is. So there's one particular area that I recommended that you actually Google and that you look up. And I'm curious how many people did it. Did you guys figure out what happens to a bicarbonate when you heat it up? So for example, in one part of your lab, you had sodium bicarbonate. This is reaction 1. You had sodium bicarbonate, and all you did was heat it up, right? So I don't know if you caught on to this, but anytime you see a delta sign over an arrow, this is in your pre-lab, delta sign over an arrow just means that you're adding heat. That's what that means. So did you guys look up what happens to a bicarbonate when you heat it up? Because I kind of hope you did. And if you did, you need to cite your sources. I'm curious if anybody found a definitive answer to what one of the products is. Because you already know that water was present. It tested positive for water. When you stuck the lit splint inside, what happened? The flame went out. So that means a lot to you. First of all, it means that there's no oxygen in there. No pure oxygen, because if there was pure oxygen, you want to know what happened to the red ember? The red ember would have reignited into an actual flame in the presence of oxygen. And that didn't happen, so there's no oxygen. If there was hydrogen present, heaven forbid, but if there was hydrogen present, you know what would happen? Think back to your mini rocket lab. What would have happened? Yeah, you would have had a loud pop. It would have blown up in your face. Okay, that would have been kind of crazy and awesome, but no. So there's no hydrogen, there's no oxygen. What could have caused the flame to go out? Yes, water vapor, I get it. Water vapor was there, and that could technically take a flame out. But there was a different gas there. Okay, and what did we say? Yes, it was CO2. Good job. CO2 gas is a very common gas used in fire extinguishers. Oh, and they actually use liquid and powderized CO2 as well, which is pretty cool. All right, so we got those two, but, you know, you can't ignore the fact that you did have some sodium present, right? Where's the sodium on the product side? You can't have just elements disappearing on you, right? And another fact is that at the end, at the very end, after you heated this stuff up, there was white powder left on the bottom. So the other product cannot be pure sodium. Do you guys remember what happened to pure sodium in the presence of like just the atmosphere and then I threw water on it? Do you guys remember that? Sodium is a shiny, malleable, pure metal. And when you stick it in the presence of water, it explodes. Okay? So you cannot say that there was pure sodium left over because that would be wicked cool and awesome, right? But no. There's not pure sodium left over. So this is why I wanted you to figure out what happens to this ion. It's called bicarbonate. What happens to that ion when you heat it up? You see, the bicarbonate ion is not very stable. When you heat it up, it undergoes a very characteristic change. And I hope you looked this up. You will be citing the source that you use to figure out what the heck happens to this. So what the heck happens to that, guys? Did you kind of figure it out? Yeah, it actually turns into just regular carbonate. A regular carbonate ion has a -2 charge. So the only logic there is that a metal would cling to it. And the only metal present in the beginning was sodium, right? So if I stick sodium with this metal, you know, this metal has a +1 charge. If I stick these two together, your logic is going to come into play. And what is the balance formula for the compound that will also be made? You have to balance charges. Na2CO3. So it bicarbonates under the presence of heat will turn into carbonate. All right, and typically you'll also get some water. All right, so over here, this is Na2CO3. This was a solid, and you know that because you saw it. It was a white powder. You know this is in the form of a gas because, you know, that's just logical. You know, carbon dioxide is a gas. And you also know, what state of matter do you think was that water? I've got to ask you that. What state of matter do you think the water was in? You saw this, right? What did you see around the top of the rim of the test tube? And in fact, you took your strip, your cobalt chloride strip, and you tested that area. And I recommended to you that you actually wipe, you know, with that pink strip, or I'm sorry, with the blue strip, that you actually wipe around in that area. And what happened? It tested positive for water, correct? So what state of matter do you want to put on that? Did you see the water? Did you see little droplets of water around the rim of your test tube? Some people did, and some people did not. Kind of hard because, you know, you guys are heating that stuff up, huh? This depends, what state of matter you put here, depends on your observations. If you didn't see any water, it's a gas. But if you saw water droplets, it's a liquid. Are we clear on that? Cool. Make sure that you balance this reaction, all right, and put states of matter everywhere. What should we put for the NaHCO3 on the reactant side? What state of matter was that? It was a solid. Duh, it's baking soda, right? Solid. And then I'm not going to tell you how, but please make sure that you balance this reaction, okay? It needs to be balanced. You need to show states of matter. Put the little triangle over the top of the arrow. That's fine. All right, so in the rubric, You guys also have to indicate the evidence that you have that a chemical reaction occurred. And I think a lot of people try to get a little too creative on those answers on some of the reactions. So like, for example, on reaction 1, do you have any evidence? Because a decomposition reaction is kind of weird. You know, it decomposes, and we had to do some special tests to figure out that a chemical reaction was actually occurring. What kind of evidence did you guys say for reaction 1 specifically? Yeah, in the back. A gas was emitted. Yep, a change in state of matter is an indication that a chemical reaction did occur. Okay, so good job. Not always though, right? Like ice melting, it's still water, but in this case, yes, because we didn't see that gas at all to begin with, and it's a totally different composition than what we started with before. And we have evidence of that because, you know, it was carbon dioxide being formed, and we had water being formed, and we have proof of that. All right, so the little test strip, testing positive for the presence of water, right? We saw a color change with that test strip, so that's definitely an indication that a chemical reaction occurred. Anything else you guys want to say on that one? Any other creative answers? Okay, so that's good. That's very good. All right, reaction 2, I can't even remember what that was anymore. Do you guys remember? Magnesium strip. Okay, obvious on that one, but hard to tell what kind of chemical reaction that is, right? You saw flame, well, you saw something burning. I don't know if you saw flame, but you saw something burning, right? Presence of light, a light emission. Oh man, super cool evidence for a chemical reaction. Here's the hard part. Do you think it was combustion? Because there's a post-lab question that kind of hints to this. Your post-lab question number 1, I'm going to read it out loud. It says, do any of the reactions performed in this laboratory activity fall into more than one category of reaction type? If so, which ones? What evidence supports your categorization? All right, so kind of tough. I think this is why they asked it, is because of reaction 2, in my opinion. All right, prove me wrong. Did any other chemical reaction kind of fall into 2 categories? Yeah, not really. This is the one. I think this is the one that they meant you guys to reflect upon. All right. It's not combustion, guys. It's not combustion. Why? What evidence do I have to support that it is not combustion? Think first before you reply. What are the typical products of a combustion reaction? See, a combustion reaction usually has a hydrocarbon, and you have to burn it in the presence of oxygen. Good job. And the products are typically water and CO2. Good job, you still remember that. Hey guys, in that fume hood, and I made you take, I was very careful, I kind of hovered around the fume hood and I reminded you a bunch of times, look at what's left. What was left of your magnesium strip? Was it shiny and malleable anymore? No. What did it look like? Crumbly, white, powdery. That's right, good job. Does that sound like water and CO2? Therefore, you have evidence that the magnesium strip burning underneath that fume hood, that was not combustion. Clear on that? All right, so then what the heck was it? Well, magnesium had to combine with something because the end product was totally different. It wasn't magnesium anymore. When something burns, like the magnesium strip was, what does stuff have to burn in the presence of? And otherwise it doesn't work. It has to have oxygen. When things burn, oxygen has to be there, right? You take a magnesium strip into outer space and you try to ignite it. First of all, you're not going to even be able to ignite it because there's no flame without oxygen. So that Bunsen burner, the only reason why it was able to work is because there was oxygen present, correct? Anytime something burns, oxygen has to be there. All right, so yes, the magnesium strip was burning, but it was not classified as a combustion reaction. So I'll give you a hint. Obviously, oxygen had to be there, correct? Magnesium is a metal. Oxygen is a non-metal. Oh my gosh, aren't metals and non-metals buddies? Don't they like to make compounds? Oh yeah, that's your big hint. Guys, make sure you are balancing charges. Remember, you're making a compound, right? Anytime you make a compound, you have to check charges. All right, so big fat hints for all of you, okay? Okay, reaction 3. Don't remember what that one was. Help me out. The alcohol. That should be obvious. The formula for your rubbing, or not rubbing alcohol, it was ethanol. The formula for ethanol is in your materials list on the handout. Make sure you get the formula right. Remember, if you get a reaction that doesn't balance, like it's impossible to balance, your formulas are wrong, bro. Okay? Sound good? You'll ace that. I'm sure you'll be fine. Okay, reaction 4. That was, correct me if I'm wrong, is that the precipitate? You guys finally got to see what a precipitate looks like. And it was kind of milky, cloudy, white. Am I right? Yeah, that's a precipitate. That is a solid substance coming out of the chemical reaction. Wasn't it amazing? You started with 2 solutions and they were both clear. I don't know if you took note of that, but the starting material was clear, it was a liquid, and then when you combine them, you got this like white cloudy stuff. Let me tell you something. If you forget to label on your products which one was solid, you messed up. So look at your balanced reaction if you're there, if you've already predicted your products and stuff. Look at your products. Make sure you labeled one of them as solid, as a precipitate. All right, so that's it. And then reaction 5, the last one. Oh my gosh, wasn't that beautiful? I love this reaction. All right, so what you did is you took the copper wire and you dunked it into the silver nitrate. All right, silver nitrate was a clear solution, correct, to start? And the copper wire obviously was coppery. And I recommended that you guys just let it sit for at least 2 minutes, right? Okay, so think about those reactants just for a minute. You had solid copper. Copper, solid, you know, it was a coiled up piece of copper. So it's in the state of a solid, right? And then you added some silver nitrate. Okay, the formula for silver nitrate is in your chemical supplies, so this is no big secret here. This is the formula. But it was in the form of a solution, right? The silver nitrate was dissolved in solution. It was a clear solution. All right, guys, give me the type of reaction. Just by looking at the reactants, you can predict. What type of reaction was this? It was a single replacement. Good job. You have a pure element and then a compound. So it's obviously a single replacement. So I love this reaction because what you have to do is realize that you had solid copper to begin with, but at the end, you didn't have solid copper anymore. You see how the silver and the copper, they're going to trade places, right? So you're going to have some copper mixing in with the nitrate. You're going to have a compound of copper nitrate. And then you're also going to have like some pure silver. Guys, do you realize what that shiny stuff that coated your copper wire was? Pure silver. How amazing was that, right? Now here's a part that we have to discuss right here. The copper nitrate. You guys know that copper can have more than one charge, correct? Okay, which copper is it? Is it copper 1 or is it copper 2? And what is your evidence or, you know, to support your decision? I bet you didn't think about this, huh? But you have evidence. Go back to your observations. Did you notice that your solution was blue at the end? Your solution turned blue. That is a huge hint, because all of these ions, that those metals that can have multiple charges, some of them have color. To tell you, it's like a hint, and it tells you, that's your evidence to tell you which charge they are. So when you have metals that can have multiple charges, their color tells you what charge they are. So you would probably go to Google, be like, color of copper solutions. Wow. There's like a whole bunch of stuff here. Isn't this cool? Okay, so dig in here. And remember, if you're looking at something like this, how do you support, like, what do you have to do at the very end? Cite your sources. Looking around, there seems to be an awful lot of blue and orange. That's kind of a big hint. All right? I'm not going to tell you the answer here. You need to figure out which copper you had. Is it copper 1 or copper 2? Make sense? You're allowed to look this up, people, okay? All right, So, oh my gosh, we're getting kind of close to the end of this handout here. So coming back, we went through all the reactions. I talked about question number 1 in your post lab. That obviously has to do with reaction number 2. All right, and then for number 2 on your post lab, this is where things get really tricky. You are going to be graded on accuracy on your answers here. And a lot of students have a lot of difficulty with predicting products, balancing the reaction, right? And predicting what type of reaction it is. But guys, that's the whole point. If you get stuck somewhere on here, I would recommend you go back to your notes, maybe review a little bit, or even Google something. It's not cheating as long as you cite your sources. Don't, okay, so someone did this. Don't say friend, my friends help me. And you actually put that in your citations. My friends help me. You're not allowed to do that, guys. Could you please refer back to traditional APA format? Okay? And watch out for cheating. I did talk a lot about that. Don't do any kind of form of cheating here in the lab. This should be all you, okay? Your own formatting, your own style, your own answers, okay? All right, and then on question number 3, can I give you huge advice? Question number 3, you may want to highlight this or underline this. Hey guys, could you please make sure that you are doing chemical reactions, examples of chemical reactions, not physical. For example, for something that says production of sound, I had a student say radio. When you turn on a radio, is that a chemical process? Is that a chemical reaction occurring? No, that is an electrical potential differentiation. It's kind of like a changing of form of energy through a physical process. Okay, that's physics, honestly, that is. If you want to come to physics, I'll explain. But we need chemical reactions that produce sound. Can anyone think of like a really awesome chemical reaction that could actually produce sound? Ah, nice. Give me some examples. Go ahead. Rockets launching into outer space. Love it. Keep going. Fireworks in the sky. Heck yeah, man. I can feel it resonate in my chest, right? I love fireworks. All right, so you're on the right track, okay? When you get to part E where it says formation of a precipitate, man, dude, you've got in your post-lab questions right here, you've got some double replacement reactions that make a precipitate. And by the way, you can go back to some of your homework assignments that produce a precipitate. I mean, seriously, right? I think you're going to be just fine, guys. Please don't try to get into that physical realm. Like I have people calling ice melting. I'm like, wait a minute. When ice melts, isn't it still water? The composition of the substance did not change. So ask yourself when you're doing question number 3, did the identity of the substance change? Is it a chemical reaction? All right, everyone? That is your review of your lab. Oh, by the way, in the error section, any thought processes going on there? Guys, I really don't think there is any legitimate error in this lab. It's all qualitative analysis. You're doing observations. Am I right? Yeah, guys, there's no error no significant source of error in this lab because it's all qualitative. I got a hand? I would not skip this section. I would say there's no significant source of error in this lab because it was all qualitative analysis, qualitative observations. So don't skip the section, put it in there, and just simply say there's no, significant sources of error. Everything was qualitative analysis. Okay? Oh, by the way, don't say I, me, we, my partner, myself. Resist the temptation to put those type of words into your analysis, okay? No I, me, we, partner, that type of thing. Me, my partner. Resist that. There's always ways that you can, sneakily change the way that you say something so that you're not saying I, me, we, okay? Keep it professional. Keep your document professional. All right, let's see, what's the only other thing? Your conclusion. So let's go back to the rubric. Conclusion. It's going to sound like you're a broken record, like you're repeating yourself. That's the purpose of a conclusion. All right, so conclusion, show each reaction Balanced, you had 5 reactions. Show each of them balanced with solubility and identify the type. So all you have to say, reaction 1 was this type of reaction. Here's what it looks like. Reaction 2 was this type of reaction. Show it balanced and written out in form. Does that make sense? You will be, it feels like you're a broken record, but that's the purpose of a conclusion. Just quickly tell me what you got. That's it. What you got? What's a balanced reaction? What type of reaction? Okay, short, sweet, simple. Do not elaborate. Don't say, this was a great lab. Or the lab went very well. Nobody cares. We don't care how well it went. We just want the results, okay? Stick to keeping it professional. Do not put any of your emotions into a lab write-up. Are we clear? Don't be like, dude, reaction 1 was so cool. Reaction 5 was my favorite. Nobody cares. All right? All right, everyone. I think that pretty much goes through everything, but do you have any questions for me at this point? All right, that should be very clear then. Okay, I'm pretty sure you guys are going to ace it. You'll get your 60 points unless you forgot to get your pre-lab stamp on time. All right, so a lot of people came without their pre-lab ready to go. And if that happened, you automatically get 5 points docked for not being prepared on time. All right, that's just fair. All right, everyone, peace out then. Let's switch gears and move over to your study guide. All right, so totally switching gears here. We're now looking at the study guide. So it's been a while since you guys have done a limiting reagent problem. And I really, really think that it might be healthy for all of us to just kind of go back to that before we start looking at all the reactions, because that should be fresh in your mind. So let's go back and look at limiting reagents and that stoichiometry piece. So what I'm going to do is it doesn't matter, 27 and 28 are very similar. I'm going to go for 27. All right, so here we go. Let's get all of that. Oh, wait, too much. Hold on. That. There we go. All right. Okay, so if I have 6.59 grams of magnesium nitrate react with 8.65 grams of potassium phosphate, part A, what's the maximum amount of precipitate you can make? Part B, what's the limiting reagent? How much of the excess reactant will be left over? And if you actually made 2.56 grams of the precipitate, what's your percent yield and percent error? All right, so this is everything. This is good. This is good practice for you. So remember, stoichiometry, think way back. You cannot do anything until you have a balanced chemical reaction. Sound familiar? All right, so what is magnesium nitrate? So magnesium, Mg. Nitrate, NO3. I'm going to kind of help you out a little bit, make it go a little faster. Magnesium is element 12. What's his charge? +2, and nitrate, you can look him up. He's on your list. He is -1. So you have a +2 and a -1. Give me a balanced formula first. Yeah, parentheses, good job, and a 2. Looking good? All right, so it says magnesium magnesium nitrate reacts with potassium phosphate. All right, so I'm going to help you out. Potassium phosphate, and they're reacting together, so I'm going to put a plus sign. Potassium is K. He's element 19. He has a +1. And phosphate, he's polyatomic because he has an 8, right? Is PO4, and he has a -3. So +1, -3. Balance it. K3, PO4. All right, and they're reacting together. Can you tell me what type of reaction this is without even being told? It is a double replacement. Good job. 2 compounds, obviously ionic. Everyone's going to switch partners now. So the magnesium is not with nitrate anymore. Who's he with? He's with the phosphate. And I'll remind you of their charges. Magnesium is +2, phosphate is -3. Not a very happy couple. So what's a common multiple for 2 and 3? 6. So magnesium is +2. I'm going to make him a +6. How many magnesiums will it take? 3. All right, phosphate is -3. How many of those guys do I need to get to -6? 2. All right, so there's one of your products. Let's get the other product. All right, who's potassium's new friend? Nitrate. Okay, and I'm going to refresh your memory of the charges. Potassium is +1, and nitrate is -1. Hey, so they're set, right? Okay, so that's the very first thing you always want to check. You want to balance all of the charges of the formulas first. And then after you get all of the formulas good, what do we do now? Same steps that you're used to on that big long worksheet that we did. What do you think you should do now? Yeah, balance the entire reaction. Sound familiar? Okay. All right, so magnesium is sitting right here. There's only one magnesium sitting here. You see no subscript after the magnesium. Over here, how many you got? 3. Okay, so let's balance that out, okay? I'm going to put a 3 over here, and that gave me 3 magnesiums. Okay. All right, nitrate is a polyatomic ion. Nitrate right here, NO3. That's him. It looks like you have a 2 subscript outside of the nitrate, but don't forget about the 3 in the front. So what's 2 times 3? You have 6 nitrates. Come to your product side. Oh, there's only 1 nitrate sitting right there, so we're going to get 6 of those guys by putting a 6 in the front. All right, because you have 6 nitrates, and you also have 6 potassiums, huh? Find your potassium all on the left. How can we get 6 over here? Yeah, stick a 2 in the front. That'll give us 2 phosphates, right? But look, you see the phosphate right here? You see that polyatomic ion? You already have 2. All right, so everything's balanced out, guys. All right, so now that you have a nice, beautiful, balanced reaction, you can proceed with the actual question. And I do this all the time. I like to list the information right into my balanced reaction. So if you have 6.59 grams magnesium nitrate, so 6.59 grams of this, reacts with 8.65 grams of potassium phosphate. What is the maximum amount of precipitate you can make? Oh yeah, we didn't look at solubility yet, huh? We need to know which one of those products is a precipitate. Alright, so solubility rules once again. I'm going to kind of help you out. It says all nitrates are soluble, no exceptions, right? So I'm going to go over to this nitrate immediately and mark it aqueous. Boy, I really hope that that magnesium phosphate is a precipitate, otherwise we're screwed, right? Alright, what does it say for phosphates? Alright, for phosphates, it says that all phosphates are insoluble unless it has like an alkali metal in the front or ammonium. Am I right? Okay. Alright, so magnesium is not an alkali metal and obviously not ammonium. So thank goodness, this is your precipitate. What state of matter is a precipitate again? Solid. There you go. Alright, so we need to figure out what is the maximum amount of precipitate that we can make. So our destination is here. Looking good? Alright, how many problems do you have to set up? 2. And once we get 2 answers, what's going to be the correct answer? The lesser amount. Good job. Alright, take a minute. You may want to pause the video. You know how to do a stoichiometry problem, right? It's a traditional stoichiometry problem. We are going to end with the mass of what? The magnesium phosphate. So this is going to take you some time. You know, you're going to have to look up a lot of molar masses and stuff. Don't forget about the mole ratio, the heart of stoichiometry. That mole ratio comes from balanced reactions. And you're going to set up 2 problems. One for the magnesium nitrate and one for the potassium phosphate. Alright, so pause the video here. And let's see if you can get it rolling by yourself. Because I'm going to show you the answer in the next minute, or in the next second here, okay? So pause. Alright, it should look something like this. Okay? One of the things I want to make sure you remember is that potassium's molar mass is not 39, it's 39.1. And that can, you know, mess up the molar mass down here if you didn't do the 0.1. Alright, the mole ratios, look at the heart. Make sure your mole ratios are correct from the balanced reaction up on top. Alright. And, alright, so let's go ahead and calculate and see what we get, okay? So for the top one, I'm going to take 6.59, divide by 148.3, divide by 3, times 262.9. Alright, I get 3.89. Did everybody confirm that? Yeah? Nice. Okay, 3 sig figs because there's 3 and all the rest of them are 4. Mole ratios do not count for sig figs. So here's one of your answers. Let's check the other one. 8.65 divided by 212.3 divided by 2, and then times 262.9. Alright, I get 5.3 if you want to round 6. 5.36? Nice. Okay, so 5.36 if you round. Alright, so which one's correct? Which one's the maximum amount that you can make of your precipitate? The lesser amount. This guy right here. So this represents the maximum amount of magnesium phosphate that can be made. Okay, so that's the maximum you can make. Therefore, which reactant ran out on you? Did the magnesium nitrate run out, or did the potassium phosphate run out? What stopped the reaction? What limited the amount that you can make? The magnesium nitrate limited how much you can make. So when you come back up, this reactant right here gave us a lesser amount. Therefore, it limited how much we could make. So this magnesium nitrate is completely gone. It's gone. None left. We had to use some of this potassium phosphate to make our 3.89 grams of magnesium phosphate, right? But did we use all of it? No. So we only used some of it. Now here comes the fun part. We need to figure out exactly how much potassium phosphate we needed in order to make that 3.89 grams of magnesium phosphate. So what we're going to do is we're going to do a reverse reaction. What I'm going to do is I'm going to start with the 3.89 grams. So 3.89 grams of the Mg3PO4-2. And I'm going to work a reverse problem to figure out just exactly how much of the potassium phosphate I needed. Now here's another thought process for you, and I love doing this with my students. You know that all of the magnesium nitrate was consumed, correct? To make your precipitate? Couldn't you just take the 8.65 grams and subtract the 6.59 grams, and that would tell you how much of the potassium phosphate you used? You used. Light bulb moment, am I right? Okay, but if that doesn't make sense to you, and that would represent how much you used, and then you can figure out how much was excess from that, okay? But for now, I'm just going to show this work because you guys are used to seeing it that way. What I'm going to do is I'm going to work a reverse problem, and I will end with exactly how much potassium phosphate I needed. So this will just tell me how much potassium phosphate it took to make that much of the magnesium phosphate. And the best part is that you already have all of your molar masses kind of figured out, so doing the reverse problem is no big deal. So the magnesium phosphate, the molar mass was 262.9 per mole. Alright, let's see, mole ratio between magnesium phosphate. Let's see, this guy's 1 on the balance reaction, 1 mole. Alright, we're trying to go to potassium phosphate, that's this guy, and there's a coefficient of 2. Alright, and then 1 mole of this stuff, K3PO4, is 212.3 grams. Alright, whatever answer this is, it better be less than 8.65 grams, right? Right? Because we didn't use all of the 8.65 grams that was available to us. Alright, so let's just go ahead and solve that. 3.89 divided by 262.9 times 2 and times 212.3. Alright, I got an answer of 6.28 grams. I'm rounding to 3 sig figs. So what does that represent? How much you used, how much was needed to make that precipitate. But we had 8.65 grams available to us. Again, 8.65 grams was available, but it only needed, but we only needed 6.28 grams of it. So you just subtract to figure out, hey, how much is left over? 8.65 minus 6.28. Boosh. 2.37 grams is left over. And what was left over? Which one was it that was left over? Yep, the K3PO4. That was the reactant that we had excess of. All right, so we've answered quite a few of the problems. We figured out the maximum amount of precipitate that we can make. We figured out how much of the leftover reactant is left over. But the question gave us a specific amount that was made. It says, let's see, if you actually made 2.56 grams of your precipitate, so 2.56 grams was actually made. How much were you supposed to make? Yeah, what's the maximum that we could have made? The 3.89 grams. Do you see that? So we were supposed to make 3.89 grams. Grams could be made. But we only made 2.56. Fascinating. I want you guys to figure out something called percent yield and percent error. Two slightly different formulas. So percent yield is what you actually got, actual, over theoretically how much you could have gotten. Okay, actual over theoretical, and then times 100. Percent error is a little different. This is the absolute value of what you actually got minus what you theoretically could have gotten. Oops, theoretical. And then you just divide by your theoretical one more time. And then times it by 100. So those are your formulas. Make sure you know those for your test. Okay, you have one question for that. Alright, so what did I actually get? Which number represents what I actually got? The 2.56 or the 3.89? The 2.56. So I'm going to put the 2.56 on, oops, I'm going to put the 2.56 for percent yield. I'm going to put the 2.56 on the top. All right, and I could have made a maximum of 3.89 grams, so I'm going to put that on the bottom. And then times 100. .56 divided by 3.89 times 100. 3 sig figs, so I'm going to call this 65.8%. Got a little over half what I was supposed to get. All right, let's do the next one. The actual amount, I'm going to give myself a little room. The actual amount was 2.56. The theoretical was 3.89. And you see those absolute value brackets that I have those in? So if you get a negative number, what do? Flip it and make it positive. There's literally no such thing as negative percent error, okay? And then times it by 100. Another mistake that a lot of people do is they type it all in one step into their calculator. You do realize that the numerator is a quantity, right? It's a quantity that is being divided by 3.89. So don't just like type it all in one step. You actually should probably use parentheses around your numerator, okay? All right, so I'm going to take the I'm going to take that numerator. Hold on. And then divide it by 3.89. Okay, I get 34. If you want to round to 3 sig figs, I get 34.2%. So just make sure you're doing the math right on that one, okay? And you'll also notice, a lot of people don't know this. Do you know that percent yield and percent error are kind of opposite of each other? Take your percent yield here and add your percent error. What do you get? You get 100. That's what it's supposed to be. Your percent yield is what you got, right? How far you approached 100%. And percent error is how far away from 100% you were. Those two values are very closely tied. Does it make sense? All right, everyone. That's enough practice for now. And man, this podcast is long. Look at that. Almost a whole hour. I hope you love me. Peace out.